Hello everyone, welcome to another episode of Deep Dive Knowledge. Hello! I read the summary of your report, and I'm really intrigued by DeepMind's work on improving the efficiency of materials discovery using deep learning. Can you tell me more about the deep learning model DeepMind developed called GNoME? How does it work, and what makes it so effective in discovering new stable structures?
Certainly. GNoME, which stands for Graph Networks for Materials Exploration, is a deep learning model that DeepMind developed to improve the efficiency of materials discovery. It uses a process called active learning, where the model is trained on available data and then used to filter candidate structures. Here's an analogy to help explain how GNoME works. Imagine you have a magic filter that can quickly separate good apples from bad ones. You start by training the filter with a dataset of known good and bad apples. The filter learns to recognize the patterns that make an apple good or bad. Once the filter is trained, you can use it to quickly check a large batch of apples and separate the good ones from the bad ones. Similarly, GNoME is trained on a dataset of known stable and unstable crystal structures. It learns the patterns and features that make a crystal structure stable or unstable. Once trained, GNoME can filter through a large number of candidate crystal structures and identify the ones that are likely to be stable. But what makes GNoME so effective is that it doesn't stop there. It takes the filtered candidates and computes their energy using a technique called density functional theory, DFT. This not only verifies the model's predictions, but also serves as a feedback loop to train more robust models on larger datasets in the next round of active learning. By iterating through this process, GNoME has been able to discover over 2.2 million new crystal structures that are stable, expanding the number of known stable crystals by almost an order of magnitude. Its effectiveness lies in its ability to leverage the power of deep learning and actively learn from the data to make increasingly accurate predictions.
That's fascinating. So GNoME utilizes active learning to continuously improve its predictions by iteratively training on larger datasets. Could you explain how the training process for GNoME works? How is it able to learn the patterns and features that determine whether a crystal structure is stable or unstable?
The training process for GNoME, graph network models for predicting material properties, involves feeding the model a large dataset of crystal structures with known stability information. The model then learns the patterns and features in these structures that determine their stability or instability. To do this, GNoME uses a machine learning technique called graph neural networks, GNN. GNNs are designed to analyze and learn from data that has a graph-like structure, such as crystal structures. In a crystal structure, atoms are represented as nodes, and the connections between atoms, bonds, are represented as edges in the graph. During training, GNoME examines the features of each atom, such as its position, atomic number, and bonding information, and its connections to other atoms. It then uses this information to make predictions about the stability of the crystal structure. The model is trained to recognize the patterns and relationships between atoms and their surroundings that are indicative of stability. By analyzing a large number of crystal structures with known stability, GNoME learns to identify the essential features that determine whether a crystal structure is stable or unstable. In simpler terms, imagine GNoME as a student studying different Lego structures. It looks at many Lego structures and learns which arrangements of blocks are stable and which are not. By observing the patterns and connections between the blocks, GNoME learns to predict the stability of any new Lego structure it encounters. Similarly, GNoME learns the patterns and features in crystal structures that determine their stability or instability.
That's a great analogy. It helps me understand how GNoME learns from the data and identifies the features that determine the stability of crystal structures. Now, you mentioned that GNoME was able to discover over 2.2 million new stable structures that were not predicted by previous human chemical intuition. Can you give me some examples of these newly discovered structures and their potential applications in different technological fields?
According to the report, GNoME has discovered over 40,500 novel stable crystal prototypes. These prototypes represent new arrangements of atoms that have not been previously observed. To understand their potential applications, let's think of these crystal prototypes as building blocks. Each building block has a unique structure and composition, which gives it specific properties and behaviors. These properties can be harnessed for various technological applications. For example, one of the newly discovered stable crystal structures may have excellent conductivity, meaning it can easily carry an electric current. This property makes it suitable for use in electronic devices such as smartphones, computers, and solar panels. Another crystal prototype may have exceptional strength and durability. This makes it ideal for use in materials for construction, aerospace, or automotive industries where strong and lightweight materials are needed. There may also be crystal structures with unique optical properties, meaning they can manipulate light in interesting ways. These crystals could be used in the development of advanced optics, such as lenses, lasers, or sensors. Additionally, some crystal prototypes may exhibit specific chemical reactivity, making them useful for catalysis, which is the acceleration of chemical reactions. These crystals could be employed in the production of chemicals, fuels, or pharmaceuticals. It's important to note that while GNoME has discovered these stable crystal prototypes, further research is needed to fully understand their properties and potential applications. Scientists and engineers will conduct experiments and tests to validate and explore the practical use of these crystal structures in different technological fields.
Thank you for providing those examples. It's fascinating to think about the wide range of potential applications that could arise from the discovery of these new stable crystal structures. Moving beyond the applications themselves, I'm curious about the impact of GNoME's discoveries on the field of materials science. How does the expansion of known stable materials by an order of magnitude through GNoME's discoveries impact the field? And how does the dataset produced by GNoME enable the development of accurate interatomic potentials and the prediction of ionic conductivity?
The expansion of known stable materials by an order of magnitude through GNoME's discoveries has a significant impact on the field of materials science. It opens up new possibilities for researchers to explore a much larger space of materials and discover novel compounds that were previously unknown. This expansion in the dataset provides a wealth of information and insights into the properties and behavior of materials. The dataset produced by GNoME enables the development of accurate interatomic potentials. Interatomic potentials are mathematical models that describe how atoms interact with each other in a material. By training GNoME models on a large dataset of known stable materials, researchers can extract valuable information about the interactions between atoms and use this information to develop accurate interatomic potentials. These potentials can then be used to simulate the behavior of materials, predict their properties, and guide experimental efforts. Additionally, the dataset produced by GNoME enables the prediction of ionic conductivity. Ionic conductivity refers to the ability of ions to move through a material, which is important for applications such as batteries and fuel cells. By analyzing the dataset and identifying patterns in the behavior of ions in different materials, researchers can develop models that accurately predict the ionic conductivity of new materials. This prediction capability is valuable for designing and optimizing materials for energy storage and conversion devices. In summary, the expansion of known stable materials through GNoME's discoveries provides a wealth of data that enables the development of accurate interatomic potentials and the prediction of ionic conductivity. This has a transformative impact on materials science, allowing researchers to explore a larger material space and accelerate the discovery and design of new materials with tailored properties for various applications.
Thank you for explaining the impact of GNoME's discoveries on the field of materials science. It's clear that the expansion of known stable materials and the development of accurate interatomic potentials and the prediction of ionic conductivity have transformative implications for materials research and development. To validate the findings of GNoME, the report mentions that comparisons were made with experimental data and higher fidelity computations. Could you elaborate on how these comparisons were conducted and what they revealed about the accuracy and reliability of GNoME's predictions?